Good morning, everyone. So, in previous lecture, we have discussed about the cantilever beam and its deflection with Castigliano's first theorem. Now, we are going to discuss on the simply supported beam, cantilever frame, and portal frame. So, let's start. First, find the deflection at point D for a beam shown in the figure below using Castigliano's first theorem. Take E is equal to 200 GPa and I is equal to 160 into 10 raised to minus 6 meter raised to 4. Here they have given a single point load at point C. A and B is a simple support, and we have to find out deflection at D point. So we have to take 50 TS load at point where we are going to find out the deflection, but the value of this P is 0. So what is the solution? To find the deflection at D, applied the 50 TS load P at D. For this case, deflection is simply supported beam. Using Castigliano's first theorem, we must have to find out the reaction in the form of P. So, the reaction at A and B is the 80 plus 0.5 P and at B is 40 plus 0.5 P. How we can find out the deflection for the simply supported beam? The most important thing that we have to find out these reactions in the form of P. So now we have these two reactions. As we know, for the finding out the deflection with the help of Castigliano's first theorem, we have to make this table and take Mx and its derivation. So first segment AC, CD and BD. Here origin ACB, limit 0 to 1.8, 0 to 0.9, 0 to 2.7. Now Mx. Mx is 80 plus 0.5 P into X. Second, 80 plus 0.5 P into X plus 1.8 minus 120X. And the last one is 40 plus 0.5 P into X. Now derivation of this is 0.5 into X, 0.5 into X plus 0.9, 0.5 into X. So this is our final terms. Now what we are going to do? We are going to integrate these two multiplication and we will find out the deflection at D. That's why delta D is equal to 1 upon Ei integration 0 to L mx into del mx upon del P into dx. Now we have to put the equation value in these equations, that is delta D is equal to 1 upon Ei integration 1 upon 1 plus 1.8 80 plus 0.5 P into X into 0.5x dx, 1 upon Ei integration 0 to 0.9 80 plus 0.5 P x plus 1.8 minus 120x into 0.5x into 0.9 dx plus 1 upon Ei integration 0 to 2.7 40 plus 0.5 P into x plus 0.5 x into dx. Now we have to put the equations value of this P is 0. So we will get 1 upon Ei integration 0 to this value is 0. That's why 40x square into dx. Second 0 to 0.9 80x plus 144 minus 120x into 0.5x this one, and third one is 1 plus plus 1 upon EI integration 0 to 2.720 x square into dx. Now we have all the things. So again expand this equation. Delta D is equal to 1 upon EI 40 x cube by 3 0 to 1.8 plus integration 0 to 0.9 minus 40 plus 4 144.5.9. This is the integration that we know. This is the simple integration. So what we are going to do over here, we have to put the value of this and EI. I is 160 into 10 raised to minus 6 meter raised to 4, that we have to convert that in mm raised to 4. So finally we will get the delta D 10.47 mm downward at D point. So whenever we have this kind of simply supported beam and we want to find out the deflection, at that time we have to find out reaction in the form of P. Now we are talking about the frame, cantilever frame. So let's start the example. Calculate vertical and horizontal displacement at point C for a rigid cantilever frame shown in the figure below. E is equal to 2 into 10 raised to 5 Newton per mm square and I is equal to 3 into 10 raised to 8 mm raised to 4. Now this is our total frame with cantilever. What is done over here? Here the deflection of this column towards the right and beam towards the downward. So deflected shape is something like this. In this case we have two type of deflection. First one is horizontal and second one is vertical. So we have to find out horizontal and vertical displacement for this kind of frame. So first we are going to find out the vertical deflection, and for that we have to take vertical point load as P. Here already we have the force that is 60, so we have to take 60 as P. Now whenever we are finalize the P, we are going to make that table, and that table is segment, origin, limit, mx, del mx upon del P. CB and BA, again this is cantilever frame, so we have to directly calculate the mx instead of simply supported beam. In the case of simply supported beam, we have to first find out reactions in the term of P, but in cantilever case there is no need. Now CB and BA, origin C and B, limit 0 to 3, 0 to 6, mx minus px minus 3b minus x minus 3. So delta CV is equal to 1 upon EI integration 0 to L mx del mx upon del P into dx. Now we have to put this value minus px into minus x dx plus 1 upon EI integration 0 to 6 minus 3p minus 3 dx. So delta CV is equal to 1 upon EI px cube upon 3 0 to 3 limit 1 upon EI 9px 0 to 6. Now we have to put the value of P as 60, so we will get 1 upon EI 540 plus 1 upon EI 3240. So finally after putting the value of EI, we will get the vertical deflection at C point, that is 63 mm downwards. So in this case, the simplest thing is there. What is toughest part of this, that is mx. Once we will get mx, the whole thing is simple. Now horizontal displacement. So for the horizontal displacement, we must have to consider fictitious load P as a 0 in horizontal direction. So to find out the horizontal displacement at C, applied fictitious load P in the right direction towards the right and at C point. Now for this case, we have to again make this table segment origin limit mx del mx upon del p. So which are the segment over here? C to B and B to A. Origin C, origin B. Limit 0 to 3, 0 to 6. Here moment at x is equal to 60 into x, but it is minus. At B point, 60 into 3, that is 180, and P into x for here. Now here no P, that's why it is constant, and differentiation of the constant is 0. Here minus x. So we have this table. Now we can consider this value and get the horizontal displacement at C, that is 1 upon Ei integration 0 to L mx into del mx upon del p. Now we have all the value that put in this equation. 1 upon Ei integration 0 to 3 minus 60x into 0 plus 1 upon Ei integration 0 to 6 minus 180 minus px minus x dx. So delta ch is equal to 0 plus 1 upon Ei, this much value. Now put the value of p as a 0 in this equation, so we will get delta ch is equal to 1 upon Ei 180 x square by 2 integration 0 to 6. So putting the value of x as a 6, and we will get the 3240 upon Ei in this case. So after the putting this value of Ei, we have the value of Ei. After putting the value of this Ei, we will get horizontal displacement at C, that is 54 mm towards the right. So here we have two cases. First is simply supported beam and second one is cantilever frame. Now the portal frame, and this frame is important for us because in the essay 2 we have to solve mostly frames in all the chapters. So what exactly going to do over here? Here horizontal and vertical reactions must be find out in the form of P. So let's start. Compute horizontal displacement of support D for a simply supported frame using Castigliano's first theorem. Take Ei is equal to 60,000 kilonewton into meter square. Here our frame, that is A, B, C, D and E point over here. A and D both are hinge support. At PE 50 kilonewton force is applied towards the right. Here this is I, 2 meter, 2 meter, this is 6 meter, 2I, here I. Now what is done over here? Horizontal displacement at D. So we have to consider P over there, as we know. And due to this P and due to this 50 kilonewton force, the reaction at A, that is 50 plus P towards the left. Now we have to solve this case, but for that we have to find out the vertical reaction also. As no, this is simply supported portal frame. Now apply fictitious load P towards the right at D. So sigma MA is equal to 0, VD into 6 is equal to 50 into 2, the reaction of this case. So we will get VD is equal to 16.60 kilonewton plus, then that is upward, and VA is equal to minus 16.67, this is downward. This is P, this is 50, so reaction at A, that is leftward, 50 plus P. So these are the reactions of the frame. Clear, everybody? Now for this case, again we have to find out the, make the table, segment, origin, limit, mx, del mx upon del p, and the segment, that is AE, EB, BC, DC, origin A, E, C, D, 0 to 2, 0 to 2, 0 to 6, 0 to 4. Mx, the first, that is 50 plus P into x, it is clockwise, 50 plus P x plus 2 minus 50x, P into 4 plus 60.67 into x, and finally P into x. Del mx upon del p, that is x, 2 plus x for P. This is a raw material for us. When we are going to collect this data afterward, the mathematical steps are there. So simply what we have to do now, delta dH is equal to 1 upon Ai integration 0 to L mx, del mx upon del p into dx. So delta dH is equal to 1 upon Ai integration 0 to 2, 50 plus P into x square dx plus 1 upon Ai integration 0 to 2, 50 plus P into x plus 2 minus 50x into x plus 2 dx plus 1 upon 2 Ei integration 0 to 6 for P plus 16.67x into dx into 4 into dx plus 1 upon Ei integration 0 to 4 px into x into dx. Now we have to put the value of P is 0 in this term. So we will get delta dH is equal to 1 upon Ei 50x cube by 3, 0 to 2, 1 upon Ei integration 0 to 2, 100 plus 50x minus 50x, x plus 2 dx plus 1 upon Ei integration 0 to 6, 16.68 x into dx plus 0, because in last term there is only P in equation. So after putting the value of P as a 0, we will get this much term. Now delta dH is equal to 1 upon Ei 50x cube by 3, 0 to 2, 1 upon Ei 20x plus 100x square by 2, 0 to 2 plus 1 upon 2 Ei 66.68 x square by 2. So we will get delta dH is equal to 133.33 upon Ei plus 600 upon Ei plus 600.12 upon Ei. So we will get the value, that is 1333.45 divided by Ei, and we have the value of this Ei is equal to 60,000. So we will get 0.022 meter. So whenever we are going to convert this in mm, we will get delta dh is equal to 22 mm towards the right. Clear, everybody? So using of Castigliano's first theorem, we can get the values of deflection is like this and rotation as we know. Now onwards, from next lecture, we are going to analyze the continuous and indeterminate beams with the help of Castigliano's second theorem. And we know what is Castigliano's second theorem. So first you have to refer the theory part of Castigliano's second theorem. So we can solve the example in our next lecture. Thank you. Thank you so much.